Right, to our penultimate talk, and what you're all sitting there obviously thinking is you've just heard about ellipticals, so you're just now dying inside thinking, well, what about the converse situation? What about red ellipticals? So up next... It's the home thing something else. Let me reset. Galaxy Zoo has grown and grown and grown and spawned a whole other project called the Zooniverse, running citizen science projects around the world. And it's not just in Oxford anymore. There are 4 main groups now. One in Oxford, one in Chicago, one in Minneapolis, and one at the University of Portsmouth, which is led by Karen Masters, who's our next speaker, who's going to talk about red spiral galaxies. Karen, everyone give her a round of applause. And she has props. Yes!
Hello, thank you for having me here. It's always a pleasure for me to come to Oxford. I was an undergraduate at Oxford some years ago. Don't need to go into that, that's fine. So it's really lovely always to come back and reminisce about my student days and visit with the Oxford Galaxy Zoo and Zooniverse crew. So 10 years ago, when Galaxy Zoo launched, I was working as a postdoctoral researcher at the Harvard College Observatory. So that was it's in Boston, in the outskirts of Boston, in the United States. And as all good postdocs do, I would come into work, I would make a coffee, and then I would read the news and spend some time on the internet. For my postdocs in the room, that's not true. I was working extremely hard all the time. Anyway, one morning in July, I come in, I had my coffee, and I read the news, and I read this article on the BBC about a new project, Galaxy Zoo, and I was like, ooh, I study galaxies. At the time I was working on galaxy redshift surveys, so mapping galaxies. I was working with a person named John Hookra, sadly passed away a few years ago, but one of the real big names in mapping the universe and understanding galaxies. A lot of the real traditional morphology came from John Hookra. So I read this BBC article, I made an account, I have one of the very earliest accounts on Galaxy Zoo. I classified about 20 galaxies. I said, that was interesting. And I went and had a chat with John Hookra about it. And we've been spending a lot of time thinking about, things that happened 10 years ago this week. And I genuinely have very little memory of what John said. I think we thought it was interesting, and he said, okay, now get back to work, we've got to map some galaxies. Pretty much. So about a year later, I was looking for a job. And I was looking for a job on the south coast of the UK for family reasons. And I made a few phone calls. And it turned out there was a postdoc just about to leave Portsmouth. And that was Stephen there in the background. And so there was a spot potentially open for me to move to Portsmouth, and I discovered, much to my delight, that Portsmouth had a link to Galaxy Zoo. So University of Portsmouth has been one of the member institutions of the Slow Digital Sky Survey for some time, and those were the first set of images that went into Galaxy Zoo. And so when I moved to Portsmouth, I was interested in getting involved in Galaxy Zoo. And I was so lucky. I had such lucky timing. I came to Portsmouth about a year after the project launched. About a year after the project launched, the 1 million galaxies in the Slow Digital Sky Survey had been classified 40 times over, and there was an awful lot of effort to try to do some science. And so Stephen was leading some of that effort at the time. And as an annoying back of the conference room questioner, Stephen had discovered these red spirals and was working on red spirals, and I stick up my hand and I'm like, have you considered the effects of dust? Which must have been incredibly annoying. Anyway, so my very first paper actually was investigating the effects of dust on the colours of spirals. So this is where my first prop comes in. So I brought a model of a spiral galaxy. So obviously...
a single line.
No, I mean, and it would rotate as well, right? Yeah. Obviously, a spiral galaxy is not solid. It's more like a kind of a mist cloud where the particles of mist are stars, and it will be rotating. They're incredibly thin. My spiral galaxy doesn't have a bulge, but you'll notice something about this, right? It looks really different if I hold it this way versus that way. And that's the difference between, obviously, face-on and edge-on spirals. And if you look at a face-on spiral, because the disk's so thin, the light basically comes straight out, straight to you. It's not passing through any of the material in the disk. That's great. It's like the sun when it's high in the sky. The light comes to you straight through the atmosphere, not passing through loads and loads of stuff. But if you look at a galaxy when it's edge on, the light is coming through all of this stuff in the disk. And the light reddens, like the sun does at sunset. It's exactly the same physics that makes the sun red and makes galaxies redder when you see them edge on. So my very first paper for Galaxy Zoo was answering the annoying question I had posed, what about the effects of dust? And it turns out, it's a measurable effect. On a population scale, if you look at face-on galaxies, you look at edge-on galaxies, the edge-on ones are redder. But we can correct for this. And then I thought, well, that's kind of boring, but let's investigate the real red spirals. And the easiest way to do that, I'm a big fan of sort of, as Bob would say, our mutual boss, former boss now, let's go for the low-hanging fruit. And so it seemed obvious that looking for the face-on red spirals was the way to go. And so we made a sample of just face-on galaxies, and we tried to find the red spirals in them. And as Becky has beautifully explained what that means, when you know it's not red because of dust, you know it's red because there just aren't any blue stars. We'll put this down. I should forget that, it's not a good idea. It's red because we know there aren't any young, hot blue stars that are dominating the night. Those have all died. The hot stars die very quickly. And so those red spirals are not forming stars, or not forming significant amounts of stars. We discovered they're not that rare, and we discovered they're a really interesting stepping stone in galaxy evolution. So as you go from blue spiral, most galaxies go through a red spiral phase, and then maybe some of them get their stars all messed up and turn into a football. The football is my three-dimensional model of an elliptical galaxy, where all the stars have been messed up and it's not rotating. Yes, I'm not going to show that either. So, like Becky said, the interesting thing about this story is the breaking of the assumptions. Actually, red spirals had been known for years. You can find papers talking about red spirals from the 1970s. But the general view of expert astronomers was that spirals were blue, ellipticals were red, and you just make a division in colour and you're done. You can find papers from the year Galaxy Zoo launched talking about how good of a correlation that was, based on a sample of 13 galaxies from the Virgo cluster. So Galaxy Zoo comes in with 1 million galaxies, and all of a sudden it's not good anymore. It's not a good assumption, and we point out that colour is not the same as morphology. And that, using fancy words there, but that just is saying that the star formation history of a galaxy, while it's linked to the dynamical history, to whether it's just always calmly rotated or if it's had these mergers and things that have messed up the motion of its stars, those two things are linked, they do correlate, but they are not, you don't have to be a blue spiral and a red elliptical. You can be these other things, because they are different physics which creates the changes. So just to finish, my favourite moment in Galaxy Zoo was actually working with a summer student that we had in Portsmouth. We had him look at some images of the red spirals as we were working on the red spiral paper some years ago now. And he noticed that most of the red spirals seemed to have bars. And he came and he said, "Is that normal? Do really that many galaxies have bars in them?" And it turns out that no, it wasn't normal. It was a really weird thing. It was one of those, that's weird. It turns out that red spiral galaxies have far more bars in them than blue spiral galaxies. Astronomers had missed this before because any big statistical study of bars in galaxies, they'd used a colour cut to find the spirals and they'd just thrown away all the red spirals. Because of Galaxy Zoo, we didn't have to do that. We had blue spirals and red spirals, and we could show that red spirals were just so much more likely to have bars in them. And it turns out we're now starting to think that that bar itself might have a role to play in what has turned a blue spiral into a red spiral without any mergers and dramatic things happening to the galaxy. That bar is just helping that galaxy use up its star formation fuel more quickly and turn it red. Thank you for having me. It's always a pleasure, and that's my story.
Thanks, Karen. I have a quick question, just to take the dog to the chair. I'm told that you can fit 3 pints into a standard frisbee, but I've never actually seen it done. So can we try that after the talk? 3 pints, apparently ultimate frisbee players do it regularly, so we'll try it after the talk.
You're buying, Greg.
Okay, does anyone have any serious questions for Karen? Well, you don't have to be too serious. One up the back here.
Do the bars grow over time in a bar spiral?
So the question is, do the bars grow over time in a red bar spiral?
And the answer is quite simple, yes, absolutely. And in fact, the rate at which they grow could be different between this galaxy, spiral galaxies that have lots of gas and spiral galaxies that don't have a lot of gas. I mean, that gas, we use gas to mean atoms of neutral hydrogen floating around in space. That's the stuff that fundamentally stars are coming from.
Is there an argument against saying that the red bar galaxy is one that just hasn't had a merger, so the bar hasn't been destroyed, versus the bar actually being a red mass? Like, if a bar gets destroyed by merging,
can you repeat the question in a Kurt Williams way?
So the
sorry, yeah, just basically.
I could have said it by now. Anyway, so the question is, are the red bar spirals just galaxies that haven't had a merger that's messed up the bar? So probably not. So there's simulations that suggest that mergers trigger bars rather than destroy them. Certainly, once the merger happens and it all crashes into each other, the bar's going to get destroyed. But any kind of sort of tidal passes of galaxies is likely to trigger bars. So we actually think the bar may be triggered by sort of gentle environmental interactions. So Becky's more recent work is talking about how environment and the stuff inside a galaxy works together to make the galaxy change and evolve.
And one final question then.
So, let's say if I'm a red spiral bar, would these just be low density areas where basically not much is happening, they just kind of just start forming over time?
So the question is, how would you find a red spiral without a bar? And Sam is nodding. I think Sam wants to answer it.
So I did some work looking at galaxy voids, and basically every high mass galaxy. So voids are areas of the universe with basically no galaxies in, and every red dead galaxy in there is a red spiral.
But Sam has worked on void galaxies, and every big galaxy that you find in a void is a red spiral of some kind. But some of them have bars and some of them don't have bars, right? We find that bars are slightly more likely in higher density environments, but that's not to say that you find a bar, it's definitely a high density environment, and the converse is also not true. So it's completely not yet a solved question, what forms a bar?
Thanks, Karen. Can we thank Karen again, please?